Hello everybody. So here we are with yet another mini spot welder. This one arrived today. I didn't really have a chance to test it out well, but I already checked, and I will show you the major differences. Actually, there aren't many, but I will show you the major differences, the most relevant with respect to the BK or BL18. So these two are, the previous versions are practically identical. You will have no way of detecting the differences between faceplates and the underside. There is no difference whatsoever between the BK version and the BL. BK11, BL18-2K, BK11-1K. The insides are just the same. The only thing that's different is that the BL18 has that update, the fix post-manufacturing, which I already spoke about in my previous videos. So that should be already covered, and also all the suggestions regarding the fixes, the resistor modification, the resoldering, refluxing, and everything. Now, this one is called Bj07-1k. As you can see, it is visually different. It's a little bit smaller, and you will see why in a second. The display is on the right, and it's labeled Wise Maple. Now, removing the faceplate, first thing you can see is that it has 4 FETs, not 5, respect to the BL118. So this is the BL118, okay? As you can see, 5 FETs, 4 FETs. They are the same type model, 4N08. Let me check. 4N04. Sometimes I mess it up, but anyhow, they are exactly the same. 4N04R8. Sorry for the mix-up. I have my previous, the other one, this one here, is actually working with 4 FETs. One was burnt and I didn't replace it, and I wouldn't, because if I get another one, it would be from a different batch. So I don't know, I'm going to keep this one like this, and it's working. So the control board, the MCU board, where the microcontroller is, as you can see, is also visually different. It's much smaller. Why? They moved practically everything from this board to the main FET board, and I will show you. Here is the model, Bj07-1k. As you can see, there is actually nothing much left here. Only the MCU, which is an STM8 series family microcontroller. The buttons, the programming header, as you can see, it's still present because somehow they need to program it. And the display is exactly the same. Under the display, you can see these components that are actually also here. And as you can see, the display driver, this transistor here, and the 2 resistors and capacitor is the same. I checked the pins, and basically it's identical. Okay, there are some filter caps there. Okay, well, that's they moved, so the voltage regulator, the capacitor, and all the voltage divider resistors, which were first here, they moved them down to the main board. This is the main board. I will show you. I will just remove these two. Okay, so you can get a better look. Okay, by the way, they give you these with a lot of heat shrink on, and I suggest you cut it off, because it's better that the screw covers the metal and not the heat shrink, because that will give you also bad contact. Anyhow, as you can see here, I don't know if you see, I still have to remove it more here. Okay, that's just another thing that will improve contact. So you remove this side too. Okay. Yeah, here it's been cut. You see, flush here, and so it screws and makes good contact. By the way, these cables aren't that great, but I haven't shortened them. You can, if you want. If you're not getting powerful enough welds, you can shorten them by about 10 centimeters, though I suggest you do not do that immediately. Just check and see how it works with your battery or lipos, and then, you know, you can maybe go ahead and trim off some wire. But it's actually calculated for this length because this is a little, has a little voltage drop, and it's necessary to limit the current going through here. But okay, sometimes it's too much. I noticed that there's a lot of voltage drop. Here is the capacitor. It's a little bit smaller. It's a 2200. This one was a 10,000. So a bit of an overkill because you really don't need that much, but anyhow. Okay, the main difference which I've noticed is this. The circuit is basically the same. Just the layout has changed. Okay, what they did do is they removed completely that resistance that drives the transistor. So let me get a little point here so I can show you a little bit better. Okay, wait, maybe the light, that's better. So here you have these two transistors here are the push poles. Okay, exactly in the same configuration and the same resistance values as the other board. Then you have, this is the input transistor here. Okay, this one is the equivalent, if you check the other board of, let me pull this up, is the equivalent of this one here. Okay, and these two here, you see where I've soldered my wire to monitor the gate output, are these two here. Wait, maybe like this. Okay, 1 and 2. In fact, I get it from that emitter. It's the same. The resistors here, of course, there are 4 couples instead of 5 because they are 4 FETs instead of 5. So each gate is connected to its 30 ohm resistor, and then there's a pull down 10K here to turn it off. And a push pull here, and then you see at this point here, wait, let me see, okay, and the base of this transistor, this is actually coming directly from pin 4. They kept pin 4. The configuration is a little bit different because now both are used. From here, from this side, which drives it directly. As you can see, let me check the board again. As you can see, there is no resistor. The output, the trigger output, it's the same pin. It's pin 19. This is a 20 pin dual inline configuration. This is pin 19, and if you follow the trace, it goes directly to pin 4. There is no resistor here, and there is no resistor here either. So this comes straight down from pin 4. Here you can see the trace. Okay, this little via here goes through. You can check it with an ohmmeter, and it just pops up and goes into the base. And so that resistor has been completely removed, and that was a better solution. It was a better idea. In fact, as we already know, removing or reducing it to 500 ohms or less is better. Actually, it's pretty mandatory. But I probably you can just bridge it out at this point. To be honest, my modification here, this version with the Arduino output, I am driving the driver of the push pull directly. I am not using any resistor here. I checked the current and it's fine, and so I guess the MCU can handle no problem. The impedance is not a problem. So that's a hint, meaning that I think you can pretty much remove the resistor there. But there is a but. The positive, that is, let's say, biasing everything, this is the output of the regulator, the filter cap. The regulator is here. This is the output, this leg here, the right leg. This is the output, and this is its filter cap, smoothing cap. While on the other version, the previous versions, let me show you the circuit here. It's a simplified version. This is the trigger coming directly from the MCU. Okay, this is kind of this is how the pin out of this board. As you can see, some pins of the other side are used too, because the voltage divider, etc., is not on the board anymore. So they had to route some of the voltage sensor and the trigger sense are on the other connector here, the 3 and 4. Okay, but as I said, the values are the same. Instead, okay, you have pin 3, you have the VCC. You see, this is 3.3, that's been changed. And on pin 5, okay, this is the ground, that's remained. While instead on pin 1 on the other board you had the positive, the VCC, here you have the manual trigger. There is a manual trigger. However, they do not give you the plug-in, they just give you the contact. Here, I'll show you. It's actually written. As you can see, it's written switch. If you bridge these two, everything is in place. If you solder 2 wires here and put a switch, it works. So that's fine. I mean, okay. But back to the driving section here. This circuit is a little bit different. While on this one, the resistor divider here, let's say the bias circuit, on the output, you see it had this 1K, 10K. This is not the 1K of the MCU output, okay? This is the 1K, 10K fix-up that they did post-manufacturing on the first board and fixed it on the second, which is exactly, I'm talking about these 2 resistors here. Oops. These 2 resistors here. Okay, this is a 1K and a 10K, these 2. These are after the 1K that is on the MCU board here. Okay, so the 1K has been removed and it comes down here. However, these were connected to, as you can see here, the plus of the battery, after the cap, of course, so after the diode. So this is protected. But that's plus 12, whatever volts you have. What they changed is they connected the plus not anymore to the cap, but to the regulator output. So you have a much lower voltage here. This is a 3.3 regulated voltage, okay? So the cap is pretty stable on the other design, so this doesn't really fluctuate a lot. But let's say that this is, let's say, a more regulated solution, because this is connected to the output of the 3.3 volt regulator. So all of this, let's say, biasing changes, because instead of having, let's say, 12 volts here, you're having 3. So the voltage here is different because the current here is different. And you can calculate that by Ohm's law, adding, this is 11K, and checking the voltage out here. However, when this is left floating, which is what is usually done, this is down to ground, okay? So, you know, this is inverting as this circuit, the trigger circuit is an inverting circuit. When this is high, this is off. When this pulses low, so let me draw, I get a pen here. So the trigger output is high, then dips and goes up again, okay? This is the trigger output. The trigger output is limited in voltage. It's because it's working from 0 to 3, and so it dips about 1 volt usually. It's not such a big dip. It's around 1 volt dip. And here you have your timing, which can go from, I don't know, 5 to whatever, 35 milliseconds, whatever, from here to here. This dip is translated, so this is the positive and this is the 0 volt here. This dip then gets translated to an opposite pulse, a much higher pulse, okay, of the same duration. This is 0 volt and this is around 11 volts. Okay, this is what I read here on this version, which is basically what I'm getting on the other ones too, after the resistor mod. So this translates to this. Now, why is this kind of critical? As I already said, if the MCU has a reset or there's a problem, this output goes down and this stays on. And that is what is making these FETs blow up, usually. Probably, I think there may be also some situation where there may be some ground looping, maybe, or some contacts on these pins which are not good, or most of the time, bad solderings. Now this board is actually, I lost it. Here it is. This board is actually soldered on pretty well. All of the components have been, I haven't touched it. I've only soldered the trigger wire here. That's all. I didn't touch any component. The solderings look good. I checked them. I checked the values. I didn't get any abnormal performance, but as I said, I've only tried it like 2 or 3 welds. The software is not the same. This is a different software. I will show you. Okay, well, just to finish the board here, there is this reverse polarity protection, let's say drain diode. So this gets charged, and when the voltage of the battery peaks low, the diode will prevent this capacitor to discharge. Now this capacitor is just powering this regulator. And so this provides enough juice for this during the pulse to stay on. And of course you have the output smoothing capacitor. So, and the biasing of these transistor is done post regulator. So let's say that's the most significant improvement. Lowering the voltage, that's why they removed the resistor. So that's what I was talking about before. 470 ohms is fine. Removing it completely, I guess you still can, because I've been doing a lot of tests with my other, let's say, Arduino fix-up, you know, the one that blew up. I removed the MCU and it's an Arduino port, and it's been working fine. But I'm probably a little bit overdriving this transistor input. However, the peaks are very, you know, limited, and so I guess I don't think there is any major problem. In this case, the voltage is much lower here because it's railed on the 3.3 rail and not the output of the capacitor, which is the battery voltage. So they removed it completely. However, the values of the resistors are the same. It's a 1K, 10K, as shown here, and that's the same, and the trigger just comes out here. So the output here, which is actually the collector, this what it does is pulls when this conducts. Okay, so you have a current to ground here, and it brings this push-pull configuration. If you look at it like this, it brings this push-pull configuration to ground. You see, and when this is low, it conducts. You see here, because this is an NPN and this is a PNP. These are the push-pull. One is connected to ground and one is connected to the positive side, okay? And the current flows through like this. Now, when one conducts, this is brought up. When the other one conducts, this is brought to ground. So that's how the push-pull configuration works. Usually they use this also in amplifiers, in classic C-class amplifiers or whatever. And it's because one turns on and one turns off. So when this is high, the current here flows. When this is low, this is off, this one's on. Okay, well, this is an inverting. It's an inverting push-pull. That's why it works on the opposite signal. This one, when this goes low, it pulls the gate high. So the gate goes here. When this is low, when this is high, it turns the gate off, meaning that this is grounded, and this is not, this is just a biasing resistor, so, and this is pulled to ground through here, so this transistor here. So I guess they improved it, and I think also putting all this circuit on the same board probably reduces other problems. Maybe some, as I said, some noise factor. Some, you know, when you weld, there's a very strong electromagnetic also pulse on the wires, and if there is some bad connection, when this when this dip happens, it can maybe disturb this push-pull, or you know, insert some noise here on this rail. I mean, I haven't seen any. As I said, I couldn't really reproduce why my FET blew. I just noticed that there was this problem with my version there, and then I also noticed that the FETs weren't being driven properly on this other, the new one, this one here, before the resistor, the R4 swap. So that's what you have to do, and there's a discussion on Reddit about that. It's been around for a while, so that's pretty much known. But this version, as I said, the big modification is that they are taking the bias voltage from the plus 3.3 volt rail, not anymore from the cap here. So that's even smoother. That might avoid, it will certainly avoid more further problems, especially if you have a fluctuating voltage. I've used some weak LiPo cells here, and the voltage, the LiPo is at, drops at, it reaches like 3 volts. It's incredible, it drops a lot. And here you have about 1 volt. And of course the welding, it's really poor. I mean, you need like 50 milliseconds for a weld, but it didn't blow up. So I guess I did this on this one, on the BL and on mine, and I did it on purpose to see if there was any problems, and with that mod, I guess there shouldn't be any other problems. And if you're sure that you check the components. So basically, these are the major differences respect to the BL version. This is a mini version. Basically the build method is the same. As you can see, it's just a little bit shorter. It has 1 FET less, but the concept and the driving circuit is basically the same, apart from those this major, let's say, modification on the biasing circuit. I can show you now the operation. It's a little bit different. The software is different. Okay, I'll just take a power supply here. Cable is a little bit short. And the negative is here. Okay, if you see, when I connect it, nothing happens. This is because this one actually, you can turn on and off using this push button. So you keep it pressed, it turns on, and this stores the last known configuration, the last set configuration. If you can see, it's slightly different, the graphics. This goes maximum to 30 milliseconds. You see, you can't exceed 30 milliseconds, which is a little bit a bummer, because if you have maybe like weaker batteries, you're not going to weld anything with 30 milliseconds. Well, maybe 0.1, but it's going to be pretty hard. I mean, as I said, I did some tests, just a few, and I noticed that when I wanted to weld like a 0.12, it was like harder with this. And I need to charge my AGM because I left it a little bit discharging. So that's also one of the major differences. These are milliseconds. It's written Q, but it's milliseconds. I checked. I have some scope shots, and these are exactly milliseconds. It goes down to 1, like the other one there. And of course you have auto and stop, you see? they introduced stop like I did. Automatically with the Arduino version, mine disarms after 30 seconds or whatever, which is not bad. Here you can actually select stop. It would have been better if maybe it did this automatically, but if you set, for example, 6 and press stop, you can keep it pressed, it will turn off, and just keep it pressed again, it will turn back on, and it will recall the last settings. If I unplug it, you will see the voltage go down because it's under the cap. Now it's off. I will plug it back on. There, and as you can see, it retains the settings. These settings are retained in the EEPROM of the STM. It has a small EEPROM inside, so you're able to save settings. Yeah, the voltage divider monitor is not so precise. Again, as I said, check it. There might be some 0.4, 0.3 difference in voltage between the real and the one that this tells you. As I said, the cap is enough. It's regulated after. So basically, this version costs, I think, as more or less as the other one. So I don't know, between the two, probably this one is a little bit manufactured better because I think it's a little bit cleaner, but I don't know, that depends, you know. It depends who made it, who soldered it together. It's very, very random. I also would suggest adding more solder and a copper wire from here to here and fluxing these 2 points. If you connect the positive side, connect them both together. You could alternatively, which is also another solution, is instead of wiring these big connectors through here, you could simply solder, if you have a better wire, keeping the distances basically the same, solder the electrode here wire directly to the positive wire, okay, and just solder this, and then bring from the battery a positive lead, just a normal thin lead, it doesn't have to be thick because there is no current going through it, to power this. So you would have this powered directly from your battery, and the positive just a straight lead. That's all. So you don't have anything passing through here, only the negative side. And this way you would have one less wire here, the thick wire is not, the high current is not passing through here. You really don't need it, and you're just powering this directly from the battery, which means that this wouldn't be subject to voltage drop, because if you measure the voltage here, you have this piece of wire where the current is passing, and the voltage, of course, will be lower here than at the battery. And that difference is about, it can be more than 2 volts, but of course it wouldn't be a problem because you have the caps and everything, but at least, you know, you're keeping this even filtered better because the battery is like a very, very big, large capacitor. So keeping this power directly from the battery and not letting the high current go through and the positive side feeling the dip, I think it's an even better solution. I think some spot welders have that actually. I've seen some that have a thick cable go through and there's just a positive lead. So that's also a smart solution, which you can modify. You can probably take, as I said, these two, cut them, just solder them together, heat shrink them, and then simply from the battery get a normal silicon AWG, I don't know, even 18, 20 gauge wire, much thinner. This doesn't, the MCU doesn't absorb anything. You can use any little thin wire, just good quality silicon, and just simply solder it. You can even solder it, you don't even need to screw it on. That way this is powered from that wire, which is together with the positive lead here. Of course, if you have one of these connectors, if you're using a LiPo, you would need to split the positive here. So you solder on 2 wires and one is coming out here. This one goes directly to your electrode, and this thinner wire would go to power your board, which is, this can be applied to any any one of these welders, because these are NMOS, and so the only switching is happening on the negative side. The positive is only merely used just to power it, and there is no need to make any current pass through this board. This is completely just, I don't know, for ease of use. But as I said, if you have a thick wire going directly to your electrode, keeping basically the same length for, you know, the same voltage drop, the two, you know, balanced, you can just power this with a thinner wire and keep this out of the way. So it's even handier. I mean, when you have the positive electrode, it's free. Okay, so I guess I will try this with when I've charged my bigger AGM battery and do some weldings and see if it's stable or not, because I always check the gate to see if there is any problem. But as I said, I didn't see any voltage drop or anything with this. The driver section, as I showed, is connected directly to the 3.3 rail, not anymore to the VCC post, even if it's post cap. So this is one of the major let's say fixes. Even if with the other method, the other older version, it can be also done probably if you just cut a trace. You would have to cut one of these traces and simply solder the wire up to the regulator, because the regulator is not here. That's a problem, and you would need to route it through maybe one of these connectors here, or pin 4, because on this board one pin is not used here. I think it's pin 2. I don't remember, one of the two, counting from the top or the bottom. I wrote it down, but okay. One of these pins is free, and these are all free. So you could actually route it through here or route it here. And then there's somebody who made another modification, a more substantial one, removing the transistors here and using an optocoupler, which is also a good alternative. Though, to be honest, I think that if this driver section here is filtered well with the caps and everything, and it's soldered well, it should work. Isolating it, physically, electrically isolating it is always good. I mean, they use it in UPSs, they use it in switching power supplies, you know, to separate the high voltage from the low voltage, the feedback circuit and everything. So, of course, it's a good practice. However, this is actually it does just one transient, and there is no high voltage involved. The only thing is the current. But as I said, the problem with all these, let's say, fast switching but not repetitive devices is that these gates have to turn on quickly and turn off. And if there is just a faulty soldering, some component that is not attached well, or some resistor that is out of tolerance or whatever, then you can have problems. That's why it's always best to check the gate performance when you do some low power welds, short welds, at least to check. But then again, it's possible to remove this circuit and put one of those 4-pin dual inline optocouplers, transistor on one side and LED transmitter on the other. The LED transmitter is the input coming from the MCU, and it can be wired. In this case, I think it was wired on the bottom. You can use these contacts here, and then on this other side where there is the transistor output, it is wired to the resistor array here. These are all pulled down, so when that is floating or not conducting, they are off. But I think it would be, I didn't check, but I think maybe you'd need to put also an additional resistor on the output of that optocoupler to pull it down, just to be sure it's turning off properly. But these are all 10Ks here on the bottom, and they are there to be sure that when the 30 ohm, when the voltage on the 30 ohm output here disappears, that these immediately turn off. So another thing that I also suggest again is to, when you receive any of these boards with a tester, check that there is no resistance, short, let's say short, okay, between the gate. If you check here, gates, these are all the gates, and between these gates, oops, you don't see the tester here. Between these gates, you should always measure 60 ohms, because 30 ohms are per gate. So they're always, if you touch these two gates, you will always measure 60 ohm. This is one gate, this is another gate, and you will see it should arrive. Oops. Yeah, well, cable was a mess. Just check between them that there are no shorts. You'll see, yeah, this tester sucks, it's very slow. You see 61 ohms, 60.9. You do this with all of them, and you will measure always 60, and then from the gate also to ground, just to be sure that it's open loop, because it's very, it's very close, and I don't know how the quality check with these are. If one of these gates is connected to ground, the MOS won't turn on. But it can disturb the operations of the other, because yeah, they're all connected, decoupled, well, not decoupled, but they have this 30 ohm resistor. So if one of these is set to ground, the other ones probably won't turn on, or if they do, they won't turn on properly, and they could break. I guess, I don't know, I didn't check grounding one. I don't think the current is enough to turn the other ones on if this is shorted to ground, but maybe it is, because yeah, they can sniff some voltage and maybe they will turn on, but not correctly, and that's when they break. So check, because I think that most of the, as I said, the failures of these kind of, let's say, cheap designs is the construction. So, I mean, I know, because I was talking with somebody and they were saying, yeah, but these are cheap, why you're spending your money on this? Okay, but the point of these videos was not to say, okay, buy this, or of course, if you spend 160 to 100 euros on a K-weld, or there are other couple of welders out there that are professional, they give you gold-plated 10 gauge cables, or even smaller, I think 8 or 6, and of course they work fine. I mean, yeah, you're spending over 200 euros. I mean, it would be absurd, right? The point was simply to investigate. I find it interesting to investigate the failure reasons for these, and maybe try to give some pointers to people who have bought these for small hobby projects, or some, maybe some fun, or if you want to spot weld some small battery packs, or fix some laptop battery or whatever. Of course, I would never suggest this for spot welding hundreds of batteries. As I said, this is nowhere, I mean, there's no, the design here is just for, yeah, it works, most kind of, but I mean, yeah, when everything is properly seated, yeah, they do work. And as I said, I think most of the failures here is because just of the cheap manufacturing, the soldering of components. If you check, you will see that you can see some solder residue between these FETs here. That's also not good. It shouldn't be there. In quality control, this stuff would be, like, what the hell is happening here? But as I said, it's not a big deal, because these are all on the same side. But if you see this, then there probably can be other problems. As I said, I did do a quick check. This version here, I find it slightly better soldered than the other versions. especially here, the components on the board here, because this is the biggest problem. But I can't vouch for all of them. That's why I'm saying that if you happen to order one of these, please don't operate it immediately. Just, you may be lucky, but don't test your luck too much. Just unscrew it, open it up, check if you can, maybe reflux if you have patience, and of course enough skill, reflux these SMD components, or at least if you have a scope, do some welds, but on a lower setting, checking the gate. Of course, one would say, yeah, but this thing should work straight away. It might. I know I've seen the first revisions. They were mostly working, not all of them, because some got destroyed, especially ones without the cap mod. A word also on that mod. There is something else that occurred to me, which I forgot. That mod places an additional capacitor on this, let's say on the older board, which unfortunately I didn't receive. I ordered a few, and I just got 2 of these, and then this model here, which I knew was different, but I was hoping it was kind of similar to the other one, but it's, as you see, totally different. That one had a 1000 microfarad capacitor put on this board because the power and the regulator and everything was here. However, and that fixed the power dip, the voltage dip here, which then avoided the reset of the microcontroller and bringing that output pin low and blowing your FETs for too long, right? That was a major failure. But also, the fact that on the motherboard, let's call this the motherboard, the FET was put before that diode, meaning that it was kind of like in parallel to the battery. That would smooth out the noise and help in that pulse, because this is a rather large capacitor. It's a 10,000 microfarad low ESR here capacitor. So for short pulses, it's a pretty large capacitor, and it might help with that little noise peak. So you would have this cap plus that cap, which actually is saving the microcontroller. And I guess that is also why, after the modifications, everybody stopped having problems with the other revision. While in this one, the cap was moved after the diode, so okay, it fixed that power dip problem. But probably on the near the circuit here, which depends more, of course, on the output of the MCU, the trigger. However, the voltage of this push-pull is the driver circuit here, the first transistor, let's call it the driver one, is dependent on the voltage of this cap, okay? And this would fluctuate. So it is smoothed out by this cap, but I don't know, it could introduce some other factor, let's call it noise, because this cap is here. It's true that it's just after the diode, but this transistor routes all the way through, and the biasing here resistors are connected to this cap, and they're not biasing connected to the 3.3 volts as this newer design here, or alternative design. So there are these differences, and the only way to tell is to do a lot of testing with the trace on the output here and on the output here with a at least a 2-channel scope, and checking the noise on a very fast pulse. I planned to do that, but honestly I didn't have time, because I work and stuff, and it takes actually several hours. But I think that can contribute. So I don't know. I mean, I think that I will continue testing the smaller one, see how it behaves. Try to drive it. Where did I put it? Oh, here it is. Try to drive it more. Maximum I have 30 milliseconds. And to be honest, 30 milliseconds isn't really much if you don't have a very low impedance battery. For example, my small motorcycle battery, it can give you a good pulse, but with these normal ones, I'm going around 30, 35. So that's basically my baseline pulse, and this is at the limit. I mean, if I try pulsing with this, it won't really weld much anything. I will try with a 5,000 milliampere hour LiPo, which I'm waiting for I got one because I have other 3S, even 4S LiPos. They're small, they're even like 50, 60 Cs, but they're too small. They're like, I don't know, 1,000. We use them for like combat airplanes or similar little pylons. So there are 4S, they have these little thick batteries, but they're very small. And I haven't tried it yet, but it's not really designed for this kind of pulses. Putting more batteries in series increases the general internal resistance, because every battery has its own internal resistance, its own impedance, of course. Yeah, you can have a 3S, right? But you have to consider that every cell it's like a little resistor inside, milliohms, I mean, from 1 to even 15 milliohms. And if you add them all up, then you get a very high internal resistance. Of course, you have a higher voltage, but then you get a higher drop, and so you're wasting more power. Basically, that's the point. So the best is to have the lowest amount of cells with the lowest amount of internal resistance. And that's why there are some spot welders. I'm actually waiting for one which have just one LiPo element, a very big one. These are 5,000 ampere hour. And they can weld pretty well. I'm curious to the ones with just the PCB. So I will try and check that one out when I receive it. But this stuff is on the way, and it takes like a few weeks at least. Okay, so I will run some more tests, and if I find something or something blows up, I will keep you posted.